Okay, greetings. I'm sorry again that I can't be with you this afternoon, but please be nice for Mr. McTeague. He's doing his best to help me out here. So what we're going to do, I had intended for us to play with the circuit scribe pens a little bit more. I had these nice resistive ones that we're going to make circuits with, but it turns out the resistive pens have just kind of become, well, pens. So that makes it a little difficult to build circuits with them. So I'm going to regroup and find something different, but in the meantime, we're going to use this interactive to get started with thinking about how to collect data to demonstrate Ohm's law. Remember, Ohm's law is this relationship between current and voltage for a resistive element. So this interactive has a whole bunch of stuff going on, but we're going to start by looking at this circuit that they've built that has a resistor, a voltmeter measuring volts, which you can see is connected again across the resistor as we saw in class, and an ammeter measuring current being measured in milliamps, voltage being measured in volts. Be careful, I know it's annoying that potential difference volt and voltage are all kind of mixed together in different things, so be mindful. Alright, there are a whole bunch of settings for this. You're going to have to go through all of them. 120 ohm resistor, a cooling fan, a light bulb, and a spool of wire. What I'm going to do, I'm going to walk you through how to do this for the resistor so we can see kind of the case that we want to compare to. We expect a resistor that has its resistance measured in ohms is probably going to be ohmic, so it's probably going to obey Ohm's law. So let's see what that looks like, so then we can ask if the other three cases, do they obey Ohm's law? So there's this whole understanding the circuit thing that you want to do in class, but I'm just going to jump right in here to trial 1. So we want to use this table and a graph to collect and analyze your data. We want to plot the relationship between current and voltage. So I want this first column to be current, which I'm going to measure in milliamps. I want my other column to be voltage, voltage, which I measure in volts. So I probably need to go and actually measure these things. Let's come up to this circuit. We're going to do the usual thing, start it playing. I can see the circuit gets turned on. There we go. So we can see it's spooling up, and as the voltage increases, so does the current. So I'm going to need to go through and just pick a couple of frames where I can see nice, easy readings. If you look closely, you can see someone's fingers up there turning a knob. So let's see. I'm going to make my voltages nice. So that looks like 1 volt to me. And let's see, that's 20, and then that's probably 5, 10, 15, 20, so that's like 10 milliamps. So 10 milliamps, 1 volt. Let's come back up here. Yeah. Zoom on up to like 2 volts. That looks like 2 volts. 2 volts looks like just shy of 20 milliamps. I'm starting to see a pattern. We'll see how it goes. Zoom on up to 3 volts. Oh, that's different. 3 volts looks more, let's see, yeah, it's 3 volts. This looks more like 27, 28. I'm gonna say 28 maybe. I don't want to go to 27.5 because I really don't have that much ability to split it. Like, it's like half of that, so it should be like 27.5, but that implies I knew it to the 10th of a milliamp, which I really don't. So let's see, 4 volts, and that looks like it's just shy of 40, so I might call that, again, like, wait, did I skip something? Nope, yeah, alright, just shy of 40. I might call that like 38. That's not 38. That's 38. Alright, so remember when we're trying to look at a relationship between two quantities, we want to get at least 5 different data points. So I'm going to try to take this as high as it can go, but now that I've got a 5th point, I know that I should have looked and see how far it goes and split up my range, but I know I need at least 5 points, so I've done all right here. So 5 volts, this looks like 45, 46. I'm going to say 46. I'm going to just keep kind of erring on the greater side. Zip on up to 6 volts. I know this is very exciting to watch. Ooh, that's back on the line. 55. Ooh. I've only got a few more of these, I hope, because I can't go up much past 10. Alright, 7 volts. 7 volts looks like 64. A new pattern seems to be emerging. 8 volts, 8 volts. 8 volts like 72, 73. Only a little further to go. Let's see, 9 volts looks like 81, 82. And the grand finale. All the way up to... That looks 10-ish. Yeah. That looks like maybe like 91, 92. Alright. So I got 10 data points. That's enough to get a good sense of this relationship. I'd certainly be able to look at it and say, is this a line? Is it not a line? So, let's look at it. That looks pretty line-ish, right? So we can add a linear regression to it. And I can see, and we gotta be careful here, this linear regression tells me it's the voltage is something times the current minus some value. We have to ask, so this value, this is the voltage when there's no current flowing. So we can ask, is that a thing that matters? We'll come back to that. And my R squared value, should call it R1 here, it's pretty good. So I've got a pretty solid linear regression here, which makes sense. These things are pretty much, no, don't want to mess with that. Pretty much right on the line. So that's pretty nice. Now, one good rule of thumb to ask about this is this 5% rule, the idea of a 5% rule. So this, my maximum value is 10 volts on the vertical axis. 5% of that is 0.5. Right? 10% of that is 1, half of that is 5%, is 0.5. So this is less than 5%. So this is pretty much supposed to be 0, so we don't have to worry too much about the physical significance of it. It is a small thing due to this not being perfectly linear, or maybe there being something happening there. So we should write this relationship as an equation. So V equals this slope times current. The units for the slope are volts per milliamp. That's confusing. Milliamp isn't a great unit to work with. You might need to make that into something different. And then the meaning of the line of the slope of the line. Well, we had this idea, Ohm's law. It said that V is equal to IR. So if I graph V and I, the slope should be R, the resistance. I just have to get the units right. That's the only tricky thing. So if I do that, I'm going to find the slope that's 0.111, yeah, 0.111 volts per milliamp. Well, milliamp is 1,000th of an amp. So I need to multiply this by 1,000 because I'm dividing by 1,000th. So it is going to be 111 ohms, which it was supposed to be 120. That's pretty decent. This is a nice example of something that is ohmic. We have a linear relationship between voltage and current, and we can get from it, if we're careful, the resistance of the resistor, and we can see that that matches pretty well. That plus or minus 5% means that we're expecting this to be between, well, what's 5% of 120? 10% of 120 is 12, so 5% is 6, so between 114 and 126. So this isn't exactly in that, but it's pretty close. It's within 10%. So if this thing was only good to 5% and we get a little bit of error in our measurement, that seems like it's a reasonable thing. All right. So in class, I want you to do the other 3 trials. You should do trial 1 yourself to make sure you're comfortable with it, because trial 1's nice, clean, and works because you just saw it work. Might want to do it, along with this. I probably should have said that at the beginning. That's unfortunate. Anyway, trials 2, 3, and 4, they're not going to be perfectly ohmic. They might behave ohmically at some times. There might be a linear bit of it, but real equipment isn't always going to behave in this ideal manner. And so that's kind of what you want to be able to talk about as you look at these trials. You want to do the same kind of thing. You want to ask, what did you plot? What does the relationship look like? Is it linear or not? If it's not linear, then you don't have a slope. You can't really analyze it in that sense. So it's just something to be mindful of. All right, good luck. Have fun. We'll build more circuits in the future.